Welcome to Echocardiography lecture series. This lecture is about artifact and it is called To See or Not to See. We'll start by showing you this case. Think of this image. This is a transesophageal video that is showing the ascending aorta and the pulmonary artery. So this is the right pulmonary artery here. This is the ascending aorta here, and we have the structure here in the lumen that we're not sure is this a dissection or it is an artifact. We'll start with reverberation artifact explanation. So this is the ultrasound probe. It will send a pulse of ultrasound here. It will hit reflector number 1 or object number 1. Then part of it will go back, be reflected to the probe here, and then we will have the image displayed here of reflector number 1. Another part of the ultrasound pulse will pass through and hit object number 2 or reflector number 2. And then it will go all the way back to the probe, and then we will have object number 2 displayed on the screen. Also, there is another part of the ultrasound power that will bounce between reflector number 1 and reflector number 2. So it will hit reflector number 1 and then come back to reflector number 2 to take the data or the imaging from here and then go all the way back. So reflector number 1 here will act like an imaging probe. It will bounce the ultrasound that will hit reflector number 2 and all the way back to the probe. So due to that delay, we will have reflector number 2 or object number 2 imaged here, but at a deeper distance due to the delay. That can happen one time, so you can have it displayed one artifact, or it can happen multiple times, so you can have multiple artifacts. And also, if we note, the distance between object number 1 and object number 2 is the same as the distance between object number 2 and its artifact. So object number 2 here is the true object, and the artifact is coming from object number 2, but it's an artifact, it's not a true object. In another word, the distance from reflector, the strong reflector number 1 here, and the artifact is twice the distance between the reflector number 1 here and the object that caused the artifact. So before we call any object that we see an artifact, we have to explain it. We should be able to explain it, otherwise we should not call it an artifact. So for a reverberation artifact, in order to call it a reverberation artifact, then we need to identify a few things. So the strong reflector that will act like a probe, we should identify the strong reflector here. And then the distance between the reflector and the artifact is always twice the distance between the reflector and the true object. So if we say this is object number 1 or reflector number 1, this is the artifact. So this is object number 2 and the artifact is here. This is the artifact. So the distance from here to here, or the distance from the reflector all the way to the artifact, is double that distance, is twice that distance. And then the true object and the artifact, they move in the same direction. So if this object is moving object here, if this is a moving object, if it moves down, then the artifact again will move down. Let's see that example that can explain more. So here we have a strong reflector number 1. You can see it bright, so it will act as a reflector here. It's bright, so it can act as a reflector. It is a possible. Then we have another reflector, which is number 2 here, that also is a bright, that can also reflect back the image to reflector number 1, or back the waves. So the wave will come from the probe here, it will hit and go back, then it will bounce back to reflector number 2, and then all the way back to the probe. So if this happens, then we will have an artifact here. That artifact represents reflector number 2. But if we measure the distance from reflector number 1 to reflector number 2, it is the same between the reflector number 2 and the artifact. Or reflector number 1 and the artifact, it is twice the distance between reflector number 1 and the reflector number 2, or the object that we are imaging, the object that is causing the artifact. And if you look carefully at the motion between reflector number 2, which is this one, and the artifact, this is an M mode. So look at the M mode here. You will see they are moving in the exactly same direction and at the same time. So you can see it going up. When this is going up, it will go down when this is going down. So exactly the same motion we will have between reflector number 2, or the true object, and the artifact. So it is important to identify the reflector number 1 and the object and the artifact, and to measure the distance between reflector number 1 and the object and the artifact, and make sure the distance makes sense, i.e. is double the distance from reflector to artifact, double than reflector to the true object, and the motion should be exactly the same motion. So if we look here again, and then we are not sure if this is an artifact or not, then let's apply the previous rules and see what happens. So I will put an M mode here and do some measurement. So sometimes post-processing we can add an M mode offline here. So here we did the measurement, and so if we look at this M mode of the previous video, and then we can identify that the strong reflector number 1 is shown here, that bright line, and then reflector number 2, or the object, is this one here. And then if we measure the distance, you can see the red line here equals the yellow line here. So now the distance from the reflector here, number 1, all the way to the artifact is double the distance from the reflector, the first reflector, all the way to the object we are imaging. So that is rule number 1. We identify the reflector. Number 2, the distance is double. And number 3, if we look at the motion, you will see that it moves down and then moves up and then moves a little bit down. So it copies the same motion of the object. If you look at the object here and you look at the artifact here, or the object that we are not sure if it is an artifact or not, then you will see exactly it follows the object. So in the previous image, what we have seen in the lumen is a reverberation artifact. Reverberation artifact can have different shapes. So for example, in this transesophageal image, we have a mechanical valve here with mechanical leaflets. So this is a mechanical valve here. So in mechanical valve, the object and the reflector might be very close to each other. So maybe we have the sewing ring, and then we have a leaflet inside, and then we have reverberation between the disc, the leaflet disc, and the sewing ring. So that very close to each other. Then you will see the artifact is coming like lines, but very close to each other. Very close to each other. Sometimes you will think it's like a continuous line all the way down, bright line, but it's a reverberation artifact. But the artifacts are recurring many times because it is bouncing between the reflector and the object many times, like this, bouncing, going and back, because it's very reflective object. It's metallic object, so it will bounce many times. So you will have 1, 2, 3, 4, 5, 6, 7, many artifacts. And we can call it a comet tail artifact, which is part of reverberation artifact. So this white line here that we see it is a comet tail artifact, and this is another comet tail artifact. The black line here is caused by the ultrasound is being reflected back from here, from the sewing ring here, all the way. All of the ultrasound is being reflected and nothing is passing through that object. So we call it shadowing artifact. It's not a reverberation, it's a shadow artifact or shadowing artifact. It's a different mechanism. If you look in the current slide, in the LV cavity, you will see some white dots that is coming inside and moving. It is a gas, it's a bubble, and we call this phenomena cavitation. And the reason I showed this because it's not an artifact, it is a true bubble gas caused by mechanical mitral valve due to the high pressure change that is caused by the quickly moving mechanical leaflet. It will cause evaporation of the dissolved gas in the blood, causing this phenomena. If you look at this video here, it has multiple artifacts. It has a reverberation artifact that cause a comet tail artifact. We can see it here, this white line, also here. Also, there is a shadowing artifact here, the black space, and some reverberation artifact or comet tail, and shadowing as well here in that area. There is a spontaneous echo contrast here, which is not an artifact. Here you can see the blood. It's caused by sticking of RBCs to each other. So the RBCs are stick to each other. They form what is known as Rollo formation. It's a pre-thrombotic changes, but it is visible, and then you can see it. Let's see this example of the artifact. It is a very common area within the ascending aorta to see a reverberation artifact. However, it can be dangerous to miss a dissection. So you can see the artifact here, or there is a line here. So in order to know if it is an artifact or not, then we have to apply the M mode. So if we apply M mode, we can then see the artifact and the object. And then sometimes the probe itself can act as an artifact. It's not always, the probe itself can act as a reflector. It's not always something you can see, but then you can always measure. First of all, if this is the object that causing the artifact, then you can see the artifact is moving in the exact direction at the exact time. So if this is going down and then up, you will see the artifact doing the same at same time. And then if you measure the distance from here to here, and then from here to here, you will find it the same. This is another example of a reverberation artifact that you can see commonly in the ascending aorta. If you look at the ascending aorta here, you will see it. It is commonly seen here, which is, an area that someone has to be careful when he's doing the exam. This is another type of artifact. If we look at the interatrial septum here, you will see as if there is two septa here. So of course one of them is an artifact, the other one is the true object, and we call this artifact here a refraction artifact that we will explain in the coming slides. So in order to explain refraction, what happens? Usually you will have a strong acoustic interface here. If you look carefully, you will see this bright line, which is strong acoustic interface. You have the main beam here, the red beam, which is went all the way to the object, then it is reflected back to the probe, and then you have the object in the correct place. The yellow beam here is a beam that went through a straight line. However, it had that strong acoustic interface, and then the angle change, it will be refracted this way. Then it will take image of that object and reflect it back to the probe, but the probe doesn't know that there is a refraction, so it will display the object in the proposed path of the ultrasound beam. So to explain it more, look at this. You have here a strong acoustic interface that should be identified before we call it a refraction. So first of thing, we have to identify a strong acoustic interface that may cause refraction. And then, if you look carefully, this refracted object or refraction artifact here, which is a pap muscle, it looks or appear lower than the papillary muscle here. But if we measure the path of the refracted beam, so the refracted beam is supposed to go all the way here, but that red beam, but it was refracted here. So if you measure this beam, you will find it exactly the same from the probe all the way to the refraction artifact. So this is another way to know it. So you need to identify the strong acoustic interface, and then you need to measure from the probe to the strong acoustic interface and then to the true object, and keep this as measurement A, and then measure from the probe all the way to the refraction artifact and call it measurement B, and they should be equal. So to identify a refraction artifact, you need to identify the strong acoustic interface and then measure the path of the refracted beam from and to the transducer, and it should equal the path of the unrefracted beam to and from the transducer, and the real structure and its artifact, they move in the same direction. This is another example. If you look at the aortic valve here, you will see almost double structure. So this is a subcostal image. It's a short axis, and the aortic valve is in the middle. You can see one here and one here. So you have a strong acoustic interface here that causes refraction. So the beam is moving, supposed to come here, but it will be refracted here and then display the aortic valve in the other place. So this is another example of refraction. This is another artifact or another type of artifact that is very interesting. So if you look at the mitral valve here, you will see two mitral valves. One appears more reflective, and the other one is a little bit less reflective. So, for example, the one here in front is more reflective, so it must be the true structure or true object, and the other one here is a little bit faint, then this is the artifact. The cause of this artifact is a side lobe artifact, and I will explain it in the coming slide. So in order to say this is a side lobe, so if this is the probe and the probe is sending image, usually the probe will send a beam. However, there will be some side beams that will be sent again from the probe, some side beams, but the probe or the machine doesn't know about that side beam. So the probe will send one beam, the main beam here, and there will be a weak, very weak side beam that will come on the side of the probe, and then it will take image of the valve. So for example, now the main beam is in this direction, so it is taking image of the atrium, but there is a side lobe that is coming on the side, and that will hit the mitral valve. But the machine doesn't know that there is a side lobe. It will think that this is part of the main beam, so it will display the mitral valve here. But because the side lobe is a weak ultrasound with a weak power, it will image, or it will show it as a faint structure. So as explained, this is the probe here, and this is the main beam, and then you have the side lobes. So again, in order to call it a side lobe, you need to identify the original object. So we need to see the mitral valve, it's there. So the main object should be identified. The distance of the imaged object by the side lobe to the transducer is the same as the distance of the artifact to the transducer. The motion is in the same direction and the same amount at the same time between the artifact and the true object. So this is another example of a side lobe. If you look here at the aortic valve, at one point it appears as double valve, but it is a side lobe. Sometimes the side lobes are not close to each other. And then, for example, in this example, you have this blue beam, which is the main beam, is imaging the left atrial cavity. And then here, because you have a bright pericardium, you have a side lobe that is imaging the bright pericardium, but the machine will interpret it in the path of the main beam, and then you will see it here. So if you measure the distance here, it will be the exact same distance here, and then you will think there is a structure within the left atrium, but it's due to a side lobe artifact. We have another type of artifact, which is a mirror image artifact, and here the strong reflector is lying behind the imaged object. So this is a strong reflector, but the image or the object that has been imaged is imaged from behind. So this is the main beam here, the blue beam, this is the main beam, and then it will hit the strong reflector, and then we'll go back to the transducer. Then part of it will hit the object from behind, and then go back to the strong reflector, and then back to the probe. So then you will see, due to that delay and imaging from behind, that object will be shown below the strong reflector. And when this object is moving, for example, if this circle is moving closer to the probe, it will be further from the strong reflector. So it will, if it moves upward, then the artifact will move downward. So now they are moving into different or opposite direction. So the distance from a strong reflector to the object is the same as the distance from the strong reflector to the artifact, but opposite direction and opposite side of artifact. So the motion is being opposite, and they lie on both sides of the strong reflector. So to call it an mirror image artifact, the strong reflector should be identified. The distance between the reflector and the artifact is always equal to the distance between the reflector and the true object throughout the cardiac cycle. Then the true object and the artifact, they move in the opposite direction. So in this example, you will see the heart as if we have two hearts. So the strong reflector here is identified, which is a bright pericardium. Here, it's very bright, and then it will start imaging the heart from behind, and then you will see mitral valve here and mitral valve here. And then you will see the infralateral wall here, which is the same as infralateral wall here. And then to go one by one and to make sure it is a mirror image art, look at that illustration. This is the infralateral wall here, and this is the infralateral wall artifact. And this is a cord artifact, and this is a cord artifact or pap muscle artifact. Anterior mitral leaflet is here, anterior mitral leaflet is here. So the distance between the reflector and the object is the same between the reflector and the artifact, and the motion is opposite direction. So if you look at that image, you will notice some lines going through the heart. You can see there is a long line here. It's not coming from that line. It's not a reverberation artifact, different size, different shape. And if you measure the distance, it will be different. But you have this line here going through the heart. And the reason for that this is an artifact. You can see the heart is moving independent of that line here. That line can be from rib space or any other structure. The reason for that is we think that the ultrasound beam is thin. It can cut. It's thin. It doesn't have any width. So this is the beam. This is the beam. It will come here, but it has a thickness. We think it doesn't have any thickness, and that thickness we call it beam width artifact. And due to that thickness, any structure that lie within the thickness of the beam will be shown in the plane as if it is in the same plane. So again, there is two types of width. We have elevation width, which is the thickness of the beam, and the lateral width. Lateral width, we know it. And we have also elevation width. So two structures, one is in front of the other, but they appear as on the same level or on top of each other. So, but they are not. And this is just to prove that this artifact, it's not a reverberation artifact. We measure the distance. One is 4.9 centi, the other one is 3.9 centi from the reflector. So if we say this is a reverberation to the probe, one is 3.9 and the other one here is 4.9. So that does not explain reverberation artifact. But if we think as if it is a beam width artifact, then yes, it is a beam width artifact. So if we look at this video here, you will see an artifact or an object that appears in the ascending aorta here. That it may be a dissection, maybe a dissection flap, or maybe an artifact, but for sure it is not a reverberation artifact, because if we say this is a reflector here, the distance here is much shorter than the distance from the reflector to the probe. So it doesn't make sense, and it moves in and out. It comes into the visible plane and then disappear. So it can be something else. So if you look at this image here, so we have a reverberation artifact within the ascending aorta. So this is a transesophageal echo of great vessels. And we think that the ultrasound beam is thin, but this is wrong. Actually, the ultrasound beam has a thickness into it, which we have seen before, the elevation width. And sometimes it will image the SVC wall, and it will appear as if it is within the ascending aorta. So you will see it coming in and out the ascending aorta. And this artifact now is a beam width artifact caused by the SVC coming into the imaging plane. So again, this is a beam width artifact that is caused by the SVC. Here we have another type of artifact. So if you look at the LV apex here, you will see that there is a hazy structure within the LV apex. We call it a near field clutter. So near field clutter is an artifact. It's caused by the high amplitude of oscillation of the piezoelectric elements in the transducer. It will appear as a hazy structure in the near field here, in the near field. It may mimic LV apical thrombus, but if you look carefully, it does not move with the heart, because the source of this artifact is the transducer, and the transducer is stationary, so it does not move. So if we look here at the LV apex, this is not a near field artifact. This is a reverberation artifact. If you look here, there is a bright object here, and the other reflector is being the probe here. So this is an artifact here. It's caused by this bright object. So the image will come here, go back to the probe, and from the probe back here and back to the probe. For that motion going back and forth, then you will see it here. Then if you measure the distance from the probe to that object, and from the object to the artifact, it will be the same. And then from the artifact all the way to the probe, it is double from the probe to the object. So it fulfills the rules of reverberation artifact. Another artifact is figure of 8 artifact. So if you look at this bright object here, it looks like figure of 8, and it is caused by ASD closure device or PFO closure device, and it's due to the nitinol mesh array or arrangement. Then we will have this type of artifact. So if you look at this nitinol arrangement of that mesh, then it will reflect the beam in such a way that you will have a figure of 8 artifact. To have a complete idea of an artifact, if you look at this 3D image, you will see some lines within the cardiac structure. So there is one line here and one line here. So we have multiple images taken during different heartbeats, and then they are stitched together. Sometimes with a respiration, it will move, or that part will move, and when stitched together, you will see this stitching artifact. So this is a stitch artifact. We see it in 3D, and it should be in multi-beat. We can see here 1, 2, and 3, and 4 beats. So this image is taken during 4 beats. In order to minimize the artifact, we ask the patient to hold the breath as much as possible, and then, or at least we do it in a single beat. But if we will take the image in multi-beat, then stitching artifact, particularly in TEE, transesophageal echo, when patient is sedated, he cannot hold the breath. Then it's inevitable. So in case if we are taking a multi-beat, for example, in this example, 4 beats, each beat will represent part of the volume. So this is beat 1, beat 2, beat 3, beat 4. See, each beat will be taking part of the volume, and then it will be stitched together, and then we will have this ugly looking stitching artifact. So let me end by showing you this video. Here we have a transesophageal echo for a patient which was done for a TE guided cardioversion. Here we can see that this is the left atrial appendage, this is left atrium, this is left ventricle, and we can see a structure here within the left atrial appendage, and that can be a thrombus or can be an artifact. But if we apply the rules of artifact, and in particular here, reverberation artifact, so that artifact, or that whatever object is here within the left atrial appendage, is likely coming from this bright object here, which is Coumadin ridge, and Coumadin ridge is a muscular ridge between the left atrial appendage and left upper pulmonary vein. So it can cause definitely a reverberation artifact. So if we measure the distance from this Coumadin ridge all the way to the probe, and then we measure it to the artifact, it will be the same, and the motion is also exactly the same. Particularly, we will see it clear if we apply an M mode here. This is the same patient from different angle, and again, it's a reverberation artifact. If you look, at the left atrial appendage, even you will see the left atrial appendage moves independently, but this object here, it follows the Coumadin ridge here. Exactly. So it doesn't move with a contraction of the appendage, but it just follows the left at the Coumadin ridge. Thank you for watching. Next lecture will be about prosthetic valves.